Welcome to The Explainer. Today, we are breaking down a genuinely mind-bending materials science paper all about something called Hempoxies 54. And look, we aren't just talking about a minor tweak to existing plastics here. This is a completely new breed of sustainable, programmable composite. We're looking at a structural platform designed to actually replace petroleum-based plastics with something you literally grow in a field, but engineered to be incredibly strong, and best of all, endlessly recyclable.
Okay, to really grasp why this is such a huge deal, we first need to confront the environmental nightmare of traditional thermoset plastics. Think about the heavy-duty carbon fiber you'd find in wind turbine blades, commercial airplanes, or even high-performance cars. They all rely on traditional epoxies to hold them together. But here's the catch. Once those epoxies cure and harden, their chemical bonds are permanently locked in place. You can't melt them down, you can't reshape them, and you definitely can't recycle them. They're basically a one-way ticket to a landfill. So the big question is, what if we could design an epoxy that was just as tough but wasn't permanent? What if it could actually adapt?
To understand exactly how Hempoxies 54 pulls this off, we're going to deconstruct it step by step. We'll cover 1. The unrecyclable plastic problem. 2. The bio-based Vitamer matrix. 3. The FGE bridge. 4. 4 scales of reinforcement. And finally, 5. Curing and recyclability. All right, jumping right into section 1, the unrecyclable plastic problem.
The entire solution hinges on a brilliant scientific concept known as Vitamers. If you think about normal plastics like a baked cake, where once it's in the oven, you can't unbake it into flour and eggs, Vitamers are completely different. They act a lot more like a structure built out of molecular Lego bricks. When you apply just the right amount of heat, these molecules can actually detach and reattach to new partners. And the crazy part? They do this without losing their overall structural integrity or network density. They keep their strength but gain this wild glass-like fluidity, which makes true recycling a reality.
That brings us perfectly to section 2, the bio-based Vitamer matrix.
Think of Hempoxies 54 as a highly programmable platform rather than just a single static material. It essentially combines two main halves: a dynamic liquid resin matrix made up of 5 distinct components, and a reinforcement side featuring 6 different carbon morphology phases that give the material its raw strength. The beauty here is that by tweaking the ratios of those matrix components and the reinforcements, engineers can precisely dial in the exact physical properties they need for any given application.
If we zoom in and look at this like a recipe, every single component has a very specific job. Epoxidized hemp seed oil, or EHO, is our bio-based foundation. Hemp seed oil is just packed with polyunsaturated fatty acids, making it an ideal base. Next up, we have zinc acetate. You can think of the zinc like a master chef. It's the catalyst that allows those molecular Lego bricks to detach and reattach later. Then there's acetic acid, which acts as the initial spark, opening up the epoxide rings so they can bond. Finally, a polyol, something like glycerol, is thrown in to control exactly how densely these molecules link together.
Moving on to section 3, the FGE bridge. This is where things get really clever.
So, how does the liquid resin actually stick to the structural carbon? That's thanks to furfuryl glycidyl ether, or FGE. This is a fully biosourced molecule that performs an incredibly elegant dual role. On one end, it has an epoxide group that permanently bonds straight into the main polymer network. But on the other end, it has a furan ring that acts essentially like molecular double-sided tape. It anchors the bioresin directly to the carbon fibers and the graphene simultaneously, without needing traditional covalent bonds on that side. It guarantees the entire structure acts as one massively strong, unified material.
Now let's talk about the muscle of the operation in section 4, 4 scales of reinforcement.
You know, a traditional composite usually just relies on one size of reinforcement, like those long carbon fibers we mentioned earlier. But Hempoxies 54 achieves its insane strength by layering in reinforcements across 4 completely different size scales. At the macro level, anything larger than a millimeter, standard carbon fiber acts as the primary load-bearing backbone. Drop down to the micro level, and microscopic biochar particles help distribute stress evenly. Go even smaller to the nano level, and tiny graphene and hemp nanosheets act like armor to stop microscopic cracks from spreading. And finally, all the way down at the molecular level, cellulose nanocrystals provide massive stiffness right at the foundational core. If you were to map this out on a logarithmic scale, it's pretty staggering. We're zooming all the way from structural carbon fibers that you can easily hold in your hand, stepping all the way down through the biochar, past the nanosheets, and arriving right down at those molecular-level cellulose nanocrystals. It's a massive spectrum of reinforcement. And remember that FGG bridge we just talked about? It's in there, spanning across all these different phases, locking every single scale tightly together.
But here's the absolute best part. The hemp plant itself provides solutions across nearly all of these scales. By using different processing methods, like controlled heating or acid hydrolysis, a single hemp crop yields both the macroscopic carbon fiber and the biochar for the structural backbone, while simultaneously providing the nanosheets and nanocrystals for that microscopic barrier stiffness. It is an unbelievably versatile feedstock that supplies almost everything this high-tech platform needs to function.
And finally, let's wrap things up with Section 5, curing and recyclability.
So how do you bake this incredible recipe? It takes a very precise 3-stage curing schedule. Step 1 is a pre-cure at roughly 90 degrees Celsius, which lets the acetic acid get to work opening the epoxide rings in the hemp seed oil. Step 2 is the main cure, hitting about 140 degrees, which completes the cross-linking and turns our liquid into a rigid solid. Then, step 3 is a post-cure blasting up to 200 degrees. This final blast of heat essentially wakes up the vitromer properties hidden inside the material. There's a magic number here, right around 140 degrees Celsius. Researchers refer to this as the topology freezing point, or the TV point. Below this temperature, the material is just a standard, solid, unyielding composite, tough as nails. But once you cross above that 140-degree threshold, those zinc-catalyzed bonds become dynamic. The molecular Lego bricks start swapping partners, and the entire network can reorganize itself without breaking apart. This exact mechanism is what unlocks its ultimate superpower, total reusability. Because of that vitromer magic, you can recycle this stuff entirely in its solid state. Say you have a damaged Hempoxies part. You literally just grind it up into small chunks, you toss those chunks into a compression mold, apply heat above that magic 140-degree line, and squeeze it with some pressure. Those dynamic bonds reach across the ground-up gaps, stitch themselves back together, and boom, you've formed a brand new solid part. The data shows you can recover up to 90% of the original mechanical strength just by doing this. That is practically unheard of for epoxies. Alternatively, what if you just want to recover those expensive, high-quality carbon fibers? You can use a chemical recycling method known as solvolysis. You immerse the cured composite in a chemical bath, like ethylene glycol, and heat it up. Because those vitromer bonds are dynamic, they'll actively trade their connections with the liquid, which completely dissolves the bioresin matrix. Then you just neatly filter out and recover perfectly intact, highly valuable carbon fibers. No more of that energy-intensive burning that the industry relies on today. This comparison hits the nail right on the head. We are fundamentally looking at a transition between two totally different eras of materials science. In the past, we had traditional epoxies, completely petroleum-based, permanently cross-linked, and basically destined to sit in a landfill forever. But now, we have Hempoxies 54, a fully biosourced matrix running on sustainable agriculture, reinforced at multiple microscopic levels, and designed from day one to be cleanly and endlessly recyclable. As we unpack all this dense chemistry and brilliant structural engineering, it really does make you step back and wonder. As we desperately try to build a genuinely sustainable circular economy, are the high-tech materials that will build tomorrow's airplanes, wind turbines, and cars simply waiting to be harvested today? It really seems like the future of high-performance composites might just be growing right now. Thanks for tuning into this explainer, and we'll catch you next time.